Alright, let's continue our step 3. We have two masses. We want to write all the forces in vector form for mass A. Let's go back to the free body diagram. Look at mass A. We have 1, 2, 3, 4, 4 different forces. So I would put an A, that's a vector, equals what? A vector can be written in something x plus something y. And I want you to look at the coordinate system we set up for mass A. Mass A, we set up our coordinate system like this, x and y, right? And NA is on x direction. However, it's pointing to the negative side of x. Therefore, my NA can be written as NAI, but make sure that's a negative because it's pointing to negative I. Here, I want to do something different. Instead of using small I, I want to use big I as the unit vector because we use big I and big Y as a coordinate system for mass A. So here, NA, we have the first force in vector form. The second force, we have weight force for block A. And if we look at the weight force WA, it's pointing downwards, straight down, vertical down, and it has an angle between x or y direction. Therefore, you need to do projection. You need to project this weight force to x and y direction. So here, since we know the angle, we know the angle of the force, right? This is our x direction and our y direction. This is the weight force WA. And angle here, what we know about the angle is theta. That's the angle of the slope. But how do you find out theta in this small triangle? And if you can see that the angle theta is actually here. Excuse me. That's your angle theta. Okay, now we know that's the angle theta, we can do the projection. So WA has a component on x direction, which would be positive. So WA and in times this should be cosine theta. And this is on I direction. Of course, WA should have another component on y direction. The positive y direction, it's pointing up the slope. However, if you look at the force WA, and the y component of WA is pointing down the slope. Therefore, that should be a negative value here. Instead of having a positive sign, you should have a negative sign for J component. This is I component. WA times sine theta J. Okay. So this should be the vector form for WA, but we know the mass for WA, so we can further simplify this by writing, replace WA with MAG cosine theta I plus AG sine theta J. Okay, let me raise the sketch here. Okay. Okay, now we have the vector form for WA, but we have more forces we want to deal with. We have friction force here, friction force for A, and I will ignore kinetic or static friction without discussing that by just looking at the equation to calculate friction force. As we all know, friction force equals mu times the normal force. Here, the normal force is NA. Okay. This force, it's a vector form, so we need to add a direction, which is unit vector. If we come back to the figure, friction force, it has the same direction, no, opposite direction as y. So here we need to make sure we add a negative sign, and here is our big J. Okay, this is the friction force. Let's move on to the next force, the tension force in the cable. It's called FTA. FTA, since we don't know the tension force, that's something we try to find out. It's gonna be FTA. The direction gonna be positive y direction, therefore it's big J, positive. Okay, so far we have all the forces for mass A in vector form. Now let's look at mass B. Go back to your free body diagram. We only have two forces in mass B. First force is WB. We can write that as mass times G. So BG. The direction gonna be, since we're looking at mass B, you need to look at the coordinate system you set up for mass B. In mass B, WB is on the opposite direction, the negative direction of small y. Therefore, here we should add J, small j as the unit vector, and add a negative sign. Another force we have is the tension force in the cable, it's FTB. And we don't know what is FTB, but we know the direction, which is on the positive J direction. Yeah. Okay, so far we finished step 3 to write